Hello, this is Programming Foundations: How Computers Really Run Code. This course builds understanding from the ground up that is necessary for you to be able to program in low-level languages. And learning low-level languages is helpful for understanding how high-level languages work. Information. This course is beginner-friendly. If you know nothing about computers, this course will teach you some things. What is computer programming? What will you learn? Computer programming means creating instructions that a computer can execute. It makes a physical device do things. This is useful for graphics, math, and miscellaneous activities that can be useful for putting your ideas into action. Before I explain all the crazy stuff in another course, I'll start with the lower level things like memory and assembly. So, let's get on with it. You will learn by the numbers I will teach you. What can programming do practically? Make games, make tools do things, make operating systems. You don't need to understand that yet. All of these are examples of programs. In the eyes of a computer, a program is its instructions. They're basically synonyms. Being able to create programs whenever you please is a nice skill to have. Vocabulary. These are words that I will refer to later in the course. Let's start at the beginning. Let's say it's 1940, probably 1 year before the first programmable computer was invented, and you have a goal: to make a tool that calculates simple math expressions like 1 plus 1 or 3 times 3. This will be similar to a modern calculator, but I will keep it simple and make it relevant to modern computing. What do we start with? Let's start with the interface. In order for a person to use our tool, it must have a visible interface so that they can send input, like pressing buttons and stuff, and get output, seeing a resulting number on some little screen, like this. Since we're only working with numbers and simple math operations, we only need buttons 0 through 9, the 4 basic operators, and equal sign to finish. Also, a button to clear the input, and a button to delete the last input character, like these two, like backspace. It's not a problem, you can set up your own keypad. It's simply 17 buttons on a panel. So, now you have a physical keypad with 17 buttons. This keypad is your interface. Very simple, a very understandable start. Storage of data. Now we need to work on giving the keypad life. There's different ways to build a calculator. A modern calculator is probably more compact and has less connections, but we will build ours in a way that reflects how common computers work. A common computer is a system of many connected devices and parts, each doing their own job. These devices can be connected via standard ports, like USB, so they can be replaced. So I'll treat our tool as such. For example, our keypad will act as its own separate device, with the job of providing user input, and it could be replaced with a different keypad at any time. This is relevant because it means we should set up a tool in a certain way, which I will explain. So, what do we need to give the keypad life? Well, let's start with storing numbers that we press. When we push a button, we want the number to be saved. We don't do the calculations instantly. We need to be able to save multiple numbers and math operators so that we can use them all later. To do a simple calculation, we need to save 2 numbers and a math operator, and then calculate it and display the answer when the equal sign button is pressed. So first, we need to add a storage device. Let's keep it simple and call it the storage device. How does data storage work? How should the storage device work? Let's figure it out. First of all, you should know that any type of information can be stored as numbers. This is because we can index anything. Indexing just means assigning something a number. For example, we can easily index the English alphabet. A equals 0, B equals 1, C equals 2, and so on. Let's say you want to store the word cab. Well, with this system, it would be 201 for CAB, not 201. It is 201. We could also index colors. Blue equals 0, red equals 1, green equals 2, white equals 3, and so on. We could do this any way we want. We just have to define it. We could define the color indexing as green equals 0, blue equals 1, white equals 2, and red equals 3, and so on. As long as you have some definition that establishes which things correspond to which numbers, you can encode things as numbers, and you can decode numbers into the original representations. For example, if we define 0 being green, and you have a 0, then you know it must be a green. If you have 0, 0, then it means green, green. So as you can see, anything can be represented as numbers. This is useful because for our tool, we won't only store actual numbers, we will also store math operators, which we can store as numbers of our choosing. So, our goal is to store numbers. How can we store numbers? You might think we could use some physical object, similar to die that has many numbers on it, and the number facing up is a currently stored number. And sure, this works. And you could easily do it yourself. You could place a bunch of dice on the ground with certain numbers facing up in order to encode a message. But it's severely inefficient for computers. So what do? We use electricity and magnets. Why? Because it's fast and reliable if we use it correctly. I'm sure you could have guessed that the answer would be electricity. We call our phones and computers electronics. So, the question now should really be, how do you store a number using electrical signals and magnets? Let's start with electricity. You might come up with the idea that we could change the strength of an electrical signal to represent different numbers. But soon you would realize this is one of the most terrible ideas known to humankind. The main reason is that electrical signal strength is not steady enough to reliably and continuously store numbers, especially with such small increments. Here's an example, an extreme example. How would you store the number 1 million? Well, if we only want to go as high as 1 million, then we would need 1,000,001 different electrical signal strengths. 1,000,001 because 0 counts as well. We don't only want 1 to 1 million, we want 0 to 1 million. So you have to count that. You would soon find out that it is impossible to keep an electrical signal strength at 1 millionth of its full signal strength potential in order to represent the number 1. Same with any other number. 2 millionths to represent 2, 3 millionths to represent 3. Natural fluctuations in signal strength happen extremely frequently, and the smaller the increment is, the higher the chance that the signal strength changes enough to represent a different number than you meant it to. In conclusion, representing a number as a signal strength does not work. Learn about number systems. So, instead, we use another method. We only use 2 signal strengths, on and off. Now, this is extremely reliable because there's a lot of room for error. Even if an on signal fluctuates, it would likely still stay on because on is represented by a large range of signal strengths. Even a 70% signal strength would still be interpreted as on, just like 100% would. If an on signal strength suddenly were to cut in half, it still might be read as an on signal. You might ask, how can we represent numbers with only 2 unique signals? The answer? We use a binary number system. What is a binary number system? First, let me explain how number systems work. A number system refers to the way we represent a number, in terms of how many unique digits there are. Using those digits, we can make an infinite amount of numbers by stacking them in different places. For example, we only have 10 unique digits, 0 through 9, but we can stack them to get numbers that are bigger than 9, such as 20. 20 just means a 2 in the tens place and a 0 in the ones place. The 2 in the tens place represents 2 sets of 10. That gives us 20. And because we have 10 unique digits, our number system is called base 10. This naming scheme works for all number systems. A number system with 6 unique digits could be called base 6. In base 6, the 6 unique digits would be 0 to 5. 0, 1, 2, 3, 4, 5. Meaning, in order to represent 6, we need a 1 in the second place. In base 6, the number 12 corresponds to the number 8 in base 10. This is because there's a 1 in the second place, which represents a set of 6, and there's a 2 in the first place, which is a 2. So 6 plus 2 equals 8. To help you understand how counting works, allow me to count 16 digits in base 10 and base 6. Remember, we include the 0, so 0 to 15 is 16 digits. In base 10, it's simple. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But in base 6, it's 0, 1, 2, 3, 4, 5, 10, 11, 12, 13, 14, 15, 20, 21, 22, 23. If you're still confused, do not look at the numbers in the way you normally would. Look at each digit individually. In base 6, 10 is not the same as R10. In base 6, 10 is just a 1 in the second place and a 0 in the first place. This is what I meant by stacking. Every increment of 1 in a certain place, or you can call it a slot, I'll call it a place, represents one full cycle of each unique number for the slot to the right. In base 10, having a 1 in the tens place means we went through a full cycle of 0 through 9 in the ones place. And having a 1 in the hundreds place means we went through a full cycle of 0 through 9 in the tens place. So, in base 10, each place really just represents how many increments of 10 were made in the place to the right. This goes for all number systems. Here's a number system illustration for our number system base 10. In order to make big numbers, you must stack cycles. So, as you can see, in base 10, the first place is the ones place, the second place is the tenth place, the third place is the hundreds place. Adding 10 ones is the same as adding 1 10. Finishing one cycle is represented as an increment, so plus 1, to the number in the place to the left. And then we must reset the counter whose cycle finished. So here we have 38, and I'm adding the 0 here, just so you know that you can represent numbers this way. 0, 38, it's just the same as 38. So if we add 1, we get 39, because we're adding this. And then if we add 1 again, notice how this resets to 0, because we don't have a digit higher than 9 that's unique. We only have 0 through 9. So it resets it, and then it adds 1 to the place to the right, to the left. Sorry. So the first place gets reset, and the second place, you add 1 to it. It represents an entire cycle in this slot. So cycle of 0 to 9 ended, right, after we added 1 to 9. So there's a 9, we added 1, reset the counter back to 0. Here's a number system illustration, base 6 as an example. So same thing. We can't really call these places the ones, tens, and hundreds places though. So we can simply call them the first, second, third, and so on place, going to the left. So first, second, third, because it gets bigger and bigger to the left. So first, second, third. When we hit 6 in the first place, it turns into a 1 in the place to the left. This means that the second place is incremented, and the counter for the first place resets. So as you can see here, we have 104. We add 1 to it. We have 105. And this is base 6. There is no 6. 6 is represented by adding 1 to the place to the left. So this resets to 0, and you add 1 in the place to the left. In our number system, this would be the tens place, but again, it doesn't exist in base 6. So we'll just call it the second place. So the cycle of 0 to 5 ended after we added 1 to the 5. So we reset the counter back to 0, and we increment to the left. Here's another number system illustration for binary, aka base 2. So now that you understand number systems, let me clarify. The binary number system, binary, really is just another name for base 2. Again, it's called base 2 because it only has 2 unique digits, 0 and 1. Instead of hitting 2, when you increment a 1, it becomes a 0 and increments the number in the place to the left. So all you're doing is carrying the 1, like a normal math. So we have 10110, you add a 1 to it, 10111, and then you add a 1 to it. You're already at the max digit, so reset this to 0, carry the 1. This was already a 1 as well, so 0, carry the 1, 0, carry the 1, and then this one, you have the 1. So it turns into 1, 1, 0, 0, 0. The binary number system is good. So let me count 16 digits in base 10 and base 2, otherwise known as binary. Each time the second place changes, I change the color, just so you can see. Base 10, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, no surprise. Base 2, binary, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. As you can see, binary is a perfectly usable number system. And it's perfect for what we need, because we can represent both unique digits, 1 and 0, as the two reliable electrical signal strengths that we talked about. 1 can be on and 0 is off. Also, we can represent these two unique digits as two different magnetic polarities. That'll be important later. 1 could be up and 0 could be down. Or you can do anything you want, north and south. You can even switch them. You could say, like, you can define it as, for example, for electricity, 1 could have been off, 0 could have been on. But that's just how we defined it as a collective group of people. We just decided 1 is on, 0 is off. So, if you're still confused about number systems and the way binary works, please let me know, because you really should know this for programming. It's important so you know what your code does, especially if you're doing low-level programming or doing bitwise operations. Also, so that you know how data storage works. You gotta know how it works in order to work with it. If there is one thing that you should remember, it's that binary is just a number system with two unique digits, 1 and 0. That's it. If you ever see an array of 1s and 0s, it's probably a number in binary. Recap. Anything can be represented as a number because of indexing. This also means any collection of things can be represented as a collection of numbers. So if you have a bunch of colors, for example, all of them can correspond to a number. Just define it. Just say what it is. Next point, we represent numbers using binary, because electricity and magnets can reliably represent the two unique digits in binary. For electricity, it's on and off. For magnets, it's the polarity, which we can call up and down. So in order to store information, we just got to store a bunch of binary numbers. Building a storage device. So with our current knowledge, we can build a storage device. I won't ask to figure that out on your own. It can get a little complicated. We're going to do it the old way because I think it's simpler to understand. Nowadays, data storage takes such little space because each little magnet is super, super small. I believe they are created chemically. But anyway, let's keep it to the basics. Don't worry, the idea is the same between old method and the new method. It's just a ton of tiny magnets, or tiny capacitors, or maybe there's other ways. Don't worry about that. The magnets are just something that can represent a 1 or a 0. So let's start with a grid of magnets in the shapes of rings. Each magnet of ours will hold 1 or 2 states, up or down. That's its polarity. That's how each magnet stores its own data, 1 or 0. An electrical signal of full strength can be applied to a magnet to change its polarity, therefore changing its state. Therefore, changing the digit it represents, 1 or 0. So all we need for an efficient and fast storage system is a ton of tiny magnets, each threaded with wires so that electricity can be applied to specific wires to change its polarity, to change the magnet's polarity. Change it from a 0 to 1, or a 1 to a 0, either way. Now, you don't really need to know how everything's set up, but it could prove useful. So, allow me to explain it plainly. First of all, you can't just thread a wire through every row. If you threaded a wire through multiple magnets in a row, and then applied an electrical signal at full strength to the wire, each magnet that sits on that wire would change its state, which is not good. The same would happen vertically. It's a clever method to target only one magnet at a time. The magnets are locked in a grid, like this. Each magnet is rotated to 45 degrees so that it's diagonal, which allows 2 perpendicular wires to go through it at the same time. Each row has 1 wire going through every magnet in that row horizontally, like this, and each column has 1 wire going through every magnet in that column, vertically. I represented that by blue. So blue is columns, red is rows. I just did that so you can see it easier. So each magnet now has 2 perpendicular wires going through it. And as you can see, this gives each magnet a column and row attribute, or X and Y respectively. And also, I just want to refer back to the vocabulary that X and Y, we use the letters X and Y to represent 2-dimensional positions, column and row, or two-dimensional sizes, width and height. You could use it for other things as well, but that's what it's most commonly used for. So in the example, column and row would be x and y. X is column, y is row. Why isn't it row and column? I don't know. This is just how society defined it. It could have been anything. Anyway, back to the slide. So this would be x and y, or column and row. Anyway, we want to target a specific magnet. To do that, we get the row and column, and we apply half electrical signal strength to each of the two wires, one being the wire threaded through that row, and the other being the wire threaded through that column. This way, the row and the column will give each magnet in them a signal strength of 1/2, except for the targeted magnet, because that targeted magnet is where the two wires intersect. At that point, the half signal strengths of the two wires combine into a full signal strength, which flips the polarity of that one targeted magnet, and it does not flip the polarity of the other ones. Here's a demonstration. Let's say we want to target the magnet at 12/8. This could either be said as column 12, row 8. So here's our columns. So this is the 12th column, 8th row. Or it could mean x equals 12, y equals 8, with the origin 0, 0 being at the bottom left. It could have been anything, but for computing, let's just call this 0, 0. Do it this way. Same thing. So as you can see, column 12 lights up. So it's column 12. This one lights up. And row 8 lights up as well. So this row, this column lights up. But the electrical signal is not strong enough to flip the polarity of these magnets. Because remember, each one is only half signal strength. Not enough. But at our specified magnet, which is this one right here, the two signals intersect. They touch each other. And they combine into a full signal, which is now great enough to flip the polarity of the specified magnet. So this one right here is going to flip its polarity. And that's how we changed it from a 1 to a 0 or 0 to a 1. Though that's just how we represent it. Really, it's just changing the polarity from up to down or down to up. Using that method lets you write data to storage by flipping the polarity of magnets, making each represent a different binary number, 1 or 0. So how do we read the data? Well, we need yet another wire. This wire will sense when a magnet's polarity flips to up. This is a long continuous wire that will go through each magnet in a diagonal pattern. For some reason, I made it green so that it'd be easier to differentiate it from the other wires. Anyway, the way it works is when any of the magnet's polarity flips to 1, the green wire will receive a signal. So the way that we can use this in order to read a magnet's polarity is to flip the magnet polarity using the row and column wires, and then we read the green wire state. But now the magnet has a different state. We didn't want that. No problem. We simply flip it back. We flip it again to return it to its original state. And we have a data. Remember, the green wire receives an electrical signal when a magnet's polarity flips to 1. This means if it was previously 1, the first flip turns it into a 0 and we wouldn't receive a signal. But if it was previously 0, then the first flip turns it into a 1 and we would have received a signal. So that's it. You flip it, check if there's a signal, and then you flip it again to return it to its original polarity. Alright, have you thought about how you would write data to storage if the storage space that you want to write to already has random non-zero data stored, possibly from past events? Like, if we want to store 0001 to a placeholder in storage, and the placeholder currently has 1010 stored, then if we assume that the currently stored data is empty, so if it's 0000, then we would only flip the last digit in order to turn it into 0001. But in reality, we wouldn't get 001, simply because the current number stored there is actually 1010. So by flipping the last digit, it turns it from 1010 into 1011. We don't want that. We want it to be 0001. It's simple to resolve. We just do a check for each current digit. If the digit doesn't match what we want, then we flip it. If it does match, we do not flip it. For example, let's say we want to store the number 7 into a placeholder of length 4. First of all, we must convert 7 into a 4-digit binary number, which would be 0111. You might wonder what I just did. Why should we use 0111 instead of 111? Because 111 is 7. That's just a conversion called zero padding. All it means is adding zeros to the left of our original binary number in order to achieve a certain length so that we can write it correctly to a placeholder. Also, this was the same thing you saw in the illustrations, the number illustrations. We did it for base 10. And base 10, instead of writing 38, I wrote 038. It's the same thing. That's why we add the zeros to the left. It doesn't change the value. If we added it to the right, it would change its value. 1110 is not 7. It's 14. In our case, we want to write to a placeholder of length 4, so we need to have 4 binary digits ready. So we add the 0 to the left. Same number, but now it's 4 digits long. See, it's completely okay to store numbers into placeholders that are longer than the length of our number. Our numbers don't need to be the perfect length match, it just can't be longer than the placeholder or else it simply can't fit. The same way, you can fit an apple into a grocery bag, but you cannot fit a couch into a grocery bag. The apple is a lot smaller than the bag, but easily fits. The couch is too big, it doesn't fit. Neither the apple or the couch are the size of the grocery bag. They are not the size of the grocery bag. But it doesn't matter because for the smaller object, it can fit. Same thing here. So here's the illustration. So we have a placeholder, 1, 2, 3, 4. We want to store 7, which is 111. So we have to convert it into 4 digits long. So we just add a 0 to the left. So now it still means 7. And then now we can store it there as 0111. Also, this was for this part. The expectation is 4 zeros and then 0001. But in reality, it was 1010 and then 1011. Anyway, back to writing binary digits safely by using a check for each existing digit in the placeholder. Remember, we want to write the number 7 or 111 in binary into a placeholder of length 4. For this, we need to write the array 0111 to fulfill those 4 digits. So here's a demonstration. The first digit, this is what's stored, this is what we want. So the first digit is a 1, we want the 0, they're different. So we flip the first digit. So you can see this is wrong, so we just flip it. Second digit, 0010, we want 0111. So right now the second one, so the second digit is 0, we want a 1, they do not match. So same thing, we flip it. Third digit, 0110, we want 0111. So the third digit is actually correct, because right now it's a 1, we want the 1, so we do not flip it, we just keep it as it is. We go on to the fourth digit. It's stored 0110, we want 0111. The fourth digit is 0, but we want the fourth digit to be 1, so we flip it. So you can see it's 0, we flip it. So this is what's stored now, and it's exactly what we wanted. This is how computers write numbers to placeholders. Computers use this process to safely write numbers in case the existing data is non-zero. So computers always do it this way. Storage addresses. Right. We have successfully made a simple storage address and learned how to correctly store and how to correctly read from it. But there's still a very clear issue. Let's say you want to store a number. How do you actually do it? Well, firstly, you must convert it into binary. And then what? Where specifically in storage, in the storage device, do you write the data to? This brings us to the topic of addresses. It is exactly as it should sound. It's precisely like a house address. The chances are, if you know where someone's house address is and you go to it, they are inside the house and you found them. It's the same for data. There's no reason to constantly track where data is. All you need is to remember an address where that data should live. With a storage address, you know exactly where that data placeholder is, so you can read from it and write to it whenever you want. Don't worry, storage addresses themselves are extremely simple. It's literally just a number that corresponds to a specific magnet in the storage device. So let's say you want to store a number for later. It's a number 7. Well, you could write the number 7 to the storage address 9. So as you can see, there's a bunch of magnets. Each one corresponds to a number, and that number is just the magnet's address. So for example, this magnet is represented by the address 1. So that's how we can refer to this magnet. So if we want to write the number 7 to the storage address 9, which is this one, this is the magnet corresponding to the storage address 9. It's a 10th magnet, remember, because we have to, start counting at 0, not 1. The reason is because we don't want to waste any numbers. We always have 0 on a side, so we might as well use it. And if you don't believe me, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's the 10th one, because 0 is the first. Anyway, at a later time, you can simply read the number at the same storage address 9, and the number 7 should be there. But there's another problem. Do you know what it is? Can you see it in this diagram? Data length is real. If you haven't figured it out by now, it's data length. Data always has a length. For example, if I wanted to store the number 2, I would have to store the binary array of 1, 0. This is binary for 2. It's 2 digits long. If I wanted to store the number 16, then I would have to store the binary array of 1, 0, 0, 0, 0. That's binary for 16. It's 5 digits long. Each magnet only stores 1 digit because each magnet has a polarity, and the polarity defines the digit. So up is 1, down is 0. If I use, each magnet only stores 1 digit. To store the number 16, which is 5 digits long in binary, you need 5 magnets. Here's a nice little illustration. If you have something that's 3 digits long, you need 3 magnets. So it's these 3. You must know the length of the data in order to retrieve it correctly. For example, let's say you have 2 data placeholders that you define with a storage address each, and both storage addresses are really close together. Let's say that data 1 is 3 digits long and reads 101. This illustration corresponds to this, so it would be this one. So if this is data 1 and it's 3 digits long, it could be, just as an example, the memory addresses 91, 92, and 93. And if data 2 is 2 digits long and reads 10, if it's next to it, it would look like this. So immediately after the last digit of data 1, immediately after we have the first digit of data 2. So data 1, data 1, data 1, data 2, data 2. So here's one array of numbers, here's a second array of numbers, right next to each other. If I use data 1's storage address, which is just the first address, so 91, and I read 5 digits, then I would read 10110, because it would first read the 101 for data 1, and it would read the 10 right after it, which is for data 2. This is completely unsafe. So, in order for you to write to and read from a data placeholder, you need to define it by 2 things. A storage address, which is the address of the first digit, he is the leftmost digit, and a data length. How many digits make up the binary number? Therefore, how many magnets? So remember, each magnet represents one number. So this is one magnet, this is one, this is one, this is one, and this is one. So 5 magnets in total here. When you know those 2 things, you can safely read and write the binary number spanning the space of the data placeholder. Here's an example. I want to store the number 7. So I'll first define a placeholder by choosing storage address 80. Here's a little illustration. So let's say we're using 80. And the data length is free. Because 7 in binary is 111, which is 3 digits long. That's all I need. So I'm just defining it as being 3 digits long. Since address 80 is my starting point and it contains my first digit, then my second digit will be address 81. And my third, last digit, will be address 82. So I would reserve 80, 81, and 82 for my data placeholder that I'm defining, which I'm going to assign with the number 7. So remember, 7 is 111. So all of them are going to be a 1. Address 80 would be 1, 81 would be 1, and 82 would be 1. So the polarity of all these are up, as you can see by the arrow. Up, up, up. When I want to read my number again, all I have to do is read 3 digits, the placeholder length, at the storage address that I defined, which is, remember, it acts as the address of the first digit, which is 80. That's the storage address. So I just read addresses 80, 81, and 82. Now I just want to clear something up. Define the placeholder, write the number spans the space of the placeholder. Just make sure you understand. You need to remember we can always change our data. We only define placeholders by address and length. The data itself can be whatever we want. We can always change it. We can write any number we want to the placeholder as long as the number we write does not exceed the placeholder's length. For example, if we have a data placeholder that we define to have a length of 2 digits, then the only numbers I can possibly store are 00, 01, 10, and 11, which corresponds to the base 10 numbers 0, 1, 2, and 3, just for your knowledge. I cannot store the number 4 in that placeholder. 4 is 100 in binary, 3 digits long, 100. That's too long to be written to the placeholder, which we defined as only being 2 digits long. Now, of course, you physically could write a longer digit number starting at the first address, but it wouldn't be read properly because we expect the number in the placeholder to be 2 digits long. We defined it as such. So you can see here, if we have just a placeholder that's 2 digits long, then you could write data outside of that. So like 50 could be something, you could write 53, but it's not safe. It's better to define a place and then use it. So 2 digits. So only store 2 digits, read 2 digits. And here's another example. This one's 5 long. So you can store 5 digits and you can read 5 digits. We define it. That's how we know how to read from it. Define? You've seen me use the word define a lot. What does that mean? You might be wondering why you have to define anything. Why not just allow placeholders to change the data length so that we can store differently sized numbers? The answer is it's because you need to remember you are not going to be managing a tool's storage. If you're going to do it yourself, you might as well calculate those numbers completely on your own. The point of the tool is to have it do things for us. And for that to happen, it needs to have instructions. See the problem here? If you want to store data, then you need to hard code storage data into the instructions so that the tool will know where to find the data. And you also need to hard code the placeholder lengths so that the instructions can read from the placeholders correctly. Now, sure, you could always change the instructions later, but while the instructions are being executed, you cannot change them. It's just the way physics works. Like, if you're reading something, if a computer is reading something, processing unit, it cannot be changed while it's being executed. This is why you need to define things. How would you feel if someone told you to watch the backpack for a moment and they come back 5 minutes later and yell at you for not watching the bike? Well, you would feel confused and upset probably. Understandably so. If you received instructions that were to watch the backpack and they leave, it's unreasonable for them to assume that you'll stop watching the backpack and start watching the bike. Because your received instructions were not to watch the bike. The instructions were to watch the backpack. Remember, this is a programming course. You are learning how to program, and programs are just instructions. Instructions can only do what you tell them to do. You can't make the instructions read from or write to placeholders in storage without defining those placeholders by the two rules, address and length. It must know those two things in order to function properly. You must define those things in order for the instructions to use them properly. Just imagine it, like, if you are the thing that's executing the instructions and you weren't given the length of a placeholder, then how would you know how many digits to read? You wouldn't. That's why you'd need the length. So you have to give the instructions, the address and the length of the data. I'm not upset, by the way. I just want to make sure you understand why we define things in programming. We have to. It's how instructions know what we want them to do. Storage types. So now that you understand how data storage works, how it looks, how you can define placeholders in it, how to read from and write to those placeholders, let's discuss the two main types of storage. So far, I've simply been calling it storage, so as not to confuse you. And I'm correct to call it storage. It stores data. But there are two main types of storage that are good at doing different things. They are called volatile and non-volatile storage. Volatile means the data is lost when power is lost. So, volatile storage. This storage is fast. Writing and reading is a lot faster for this type of storage than it is for non-volatile storage. The catch is that all the data is lost when the power is gone. If there's a power outage, the data will disappear. It'll be gone. Non-volatile storage. Storage is slow. Reading and writing is a lot slower for this type of storage than it is for volatile. The upside is that all the data is not lost when power is lost. The data persists. It will not disappear no matter how long it is kept unpowered. I mean, you could keep a non-volatile storage system in a garage for 15 years. The data will be fine. Unfortunately, we cannot have best of both worlds. We just can't have storage that is both really fast and safe from power loss. Why? It's just physics. It's a trade-off. Don't worry about that. So, what is each one useful for? Volatile storage is useful for anything temporary. This includes calculations, temporary data, cache, graphics, anything that can be lost without consequence. So, since losing temporary data doesn't really matter, it might as well be fast. Non-volatile storage. It's useful for important information. This includes files, program instructions, configurations, anything where losing it would be bad. We would rather protect this type of data from power loss than have it be fast and lose that protection. So it's just a trade-off. It's okay that it's slow because we're protecting it from power loss. It will not disappear. The main type of device for volatile storage is RAM, random access memory, or just called memory. It's usually thin or small. It uses electronic capacitors. I actually drew everything in this presentation. I drew all the illustrations. I drew all of them. So I drew this. Yeah, this is RAM. This is what a RAM card looks like. It's green. There's a bunch of pins and all these other things that actually contain the capacitors that store the data. Remember, it's volatile. So if you lose power, it's gone. But the upside is that's fast. And then the main type of device for non-volatile storage is HDD, hard disk drive, and that's this one. An HDD is bigger and heavier because it contains magnetic platters. So the platters are circles, and there's a bunch of them. And then this is the reader. It's like a triangle. It goes to a point and it reads things. HDD, RAM. Remember, there's a lot of different types of storage. These are just the main ones that you'll see in common computers, for example. RAM, HDD. So, which storage type should our tool use? Our tool is a simple calculator. Does it need to store files? No. Does it need to store configurations? Not really. But does it need an initial instruction set? Yes. We actually do need some type of non-volatile storage device to store the initial instructions so that the tool doesn't lose those instructions just because it has no power. We don't need much non-volatile storage at all. Our tool will be very simple. Next question. Is there temporary data store? Yes. We have things like inputted numbers, math operators. These things can disappear without consequence. We don't care. So we might as well make those things fast by using volatile storage. But we don't need much of that either. Our tool will be simple. So let's add the two devices to our tool. Right now, we just have the keypad as an interface. Let's add an extremely small RAM block. So it's volatile and it's fast temporary data, and we'll add an extremely small ROM, read-only memory block, which is non-volatile and slow. By the way, even though these acronyms look really similar, ROM and RAM, they are not related. Remember, RAM is random access memory. ROM is read-only memory. Different things. The ROM acts as the non-volatile storage. So let's not connect anything yet. Just imagine a table with all three on it. Here's a little illustration. So here's a keypad. And then these are like the relative sizes. So if this is like a normal keypad, it can fit in your hand maybe. The ROM is about this size. The RAM is a lot smaller. And that's data storage explained. I hope that you all enjoyed this course and that you learned something. Remember, the main topic of this one is data storage, or you can call it memory. Just remember the main points, the way to store data, so as numbers in binary, the way it physically works, which is it's just a bunch of capacitors or magnets. In my example, I use magnets, and a lot of conventions, like you need an address and length to store and read data correctly, stuff like that. All right, see you in the next one. Bye.